So how many people have heard about Kinetic before? How many people? Traitor. How many people have never heard of Kinetic before? Everybody has. So I'm going to go through this quickly, and then I'm going to have a sort of in-depth discussion on the security features of the protocol and of the drive itself. You've all seen this, I assume. What I love about this is both the title, but a hard drive with an Ethernet interface and an object-style API. We really believe it's both items that really provide value because it allows us to do things in the drive much better than are currently done. How many people know what SMR is? Right? How many people think it's an easy thing to work with? A drive is no longer random write. It's sequential write only. And every once in a while you can get a random gap in there, but in general the drive is sequentially written. And in that case, you really have to think about how you're doing your file systems and change the entire world. Well, if you're going to change the entire world anyway, why don't you go ahead and change it to an interface that's a little smarter than sectors? So, and that's what we've done, and it's a combination of an Ethernet interface and a key value API. Where's my case? It's a normal drive. Normal drive has a normal controller board on it. On that board is an ARM processor, tens of megabytes of RAM, and some analog stuff that drives the head disk assembly. What we've done is we've added a second ARM processor that processes the Kinetic Protocol. And the value of that is that now we can have the exact same board, now with an additional processor, and we can get to market very quickly. But the value here isn't that there's a processor here that you can run code on. That's not value. That's an implementation. The fact is, there's no reason to have this link here, this SATA link between this chip and this chip, because it's just additional resources. So what we expect to be doing over time is actually taking that Kinetic API and merging it into the base product. So now you have a very cost-effective, very simple, small implementation of Kinetic, where actually in here we're taking direct advantage from the Kinetic level, direct advantage of the physics of the disk, of the way disks are written, on the way the systems are need to write to the disk. So now you take one of the Kinetic disks, you have a library above it. We have the library is a user space library, and the connection between the user space library and the drive is standard TCP/IP gigabit Ethernet. It's defined by a protocol called Google Protocol Buffers. The applications talk to the user space library. The user space library opens up a TCP/IP connection to the drive. Okay? I just love it. One time a customer said to me, "Can I get the driver?" There is no driver. Right? There's no operating system dependence. None whatsoever. So we want to be able to take the Kinetic Protocol and make it extremely fast. Make it extremely lightweight. Because the heavier it is, the more heat you have, the more expensive this drive is. So we're doing our best to cost reduce and provide these devices to thousands and thousands of people in mass quantities. The protocol is already GPL, and the libraries for C++, Java, Python, Erlang are all available open source right now. And for those of you who are interested at all, there should be a C library within a matter of weeks. That'll be a C library, both a C library you can use in a kernel of Linux or in your embedded application, or a C library that you can use in a user space in a Linux machine. Also OS X, not Windows. Darn it. Above the library is I call it the application. It could be the storage application. It could be the Hadoop application. It could be the that could be a Ceph application. It could be almost any applications, or it could be somebody that wants to build their own. Okay, someone. Oh, that's not my screen. Jesus.
That's you.
Never mind. Okay, this is the part that does application clustering and management. Because the drives themselves, we don't want to break the paradigm of drive. There's several things we don't want to break by this change. We don't want to break the paradigm of multiple vendors having support for this device. So we fully expect that there will be other proprietary solutions out there for the drives themselves. The second item is the drives do not enforce a specific style of clustering. If you go out and you look at cloud computing systems cloud storage systems around the market, there are many different styles of cloud of cloud storage systems. Whether they use Quorum, whether they use Paxos, whether they use distributed hash table, or whether they use hierarchical trees. All of those things are something that we don't want to force on customers. So we create a device that's an individual device that has features and capabilities that help eliminate that layer of servers that goes right here, but does not limit a customer on how the devices will be clustered, how they will be used. Also, this is the layer of management. This is the layer that decides whether or not this drive is still functioning. That's the layer that decides. Is that a question?
Yeah.
Yeah.
So the protocol that goes on top of the TCP IP is also open?
Yeah. Everything between here and here is open. All either GPL, the libraries are all GPL, so they're not viral. There is no clause like Berkeley DB or SleepyCat that says if you use it for commercial, we're going to come get you. There is none of that. There is also a fully functional simulator of this drive, and that simulator is available open source. Okay? Fully functional. But again, there's a system up here that adds value to customers. Think about Swift, or think about Ceph, or think about HDFS. There's a system up here that is doing the guarantees of availability. They're doing the guarantees of durability. They're doing the guarantees, and they're adding value. And therefore, it's very possible that this is where a proprietary system vendor, or an open source system, or somebody is able to make a lot of money. That's my plea is we're not trying to take your job away from you. It used to be a disk drive needed to hook directly to a computer because, well, SATA can only hook to one. SAS can hook to two. Fiber channel is fiber channel, and it's not really fun. But in general, if you have a networking protocol here, now the machine that is talking to the disk drive can be anywhere in the data center. Let's assume for a minute that this drive is a management node that's checking the health and welfare of all of these drives. If that management node goes down, well, it's on a network. You can bring it up somewhere else. It really doesn't matter. You no longer have this tether or this cable between the drives and the server it supports, so that if that server fails, who cares? In the past, with that cable, you had to rush into that data center and fix that machine, or that storage would not be available. If one machine can talk to one drive, these machines, 3 machines, can talk to one drive. And the value is that this application can serialize a data structure, write it onto the disk drive, and this machine can read that entire data structure. It's very simple. Put a key and a value, get a key, return the value. And additionally, there's atomic operations. Let's assume you had a counter down here and a value. This person gets the value, this person gets the value. This person increments the value, this person increments the value. At the same time, they both write back to the drive. One will win, and the other one will get a message that said, I'm sorry, the data you're writing is based on data that is no longer current. It's stale. Think of it as a compare and swap command where it fails. So there's atomic operations down in the drive. People have taken this technology to be able to build two-dimensional atomic structures inside of this kind of configuration. If 3 hosts can talk to one drive, 3 hosts can talk to 1,000 drives or 10,000 drives. And the clustering is, again, up at this level. And the reason why I can prove it scales, it's a very simple theory, a very simple proof that it can scale. It can scale because this drive has no knowledge of any other drive. Nice whistle. This drive has no knowledge of any other drive. Whether this system can scale, that's their problem. The drive is not a limiting factor. Additionally, we have a lot of features in the drive that help get the data moved for them. The machines that used to be here would pick up the data and move it over to another machine and put it down. Those machines are gone. But a lot of the things that the machines that were here did, those functions are now subsumed into the drive. Things like copying data from one drive to another. Now the drive can be given a list of all the keys to move to another drive. Additionally, things like background media scans, data compaction, which are things that every object storage system needs to do. We do the background media scans ourselves and report bad keys, which is a lot better than what other systems do when they report a bad sector, because you don't know what to do with that. Also, compaction. Every storage system has some kind of background compaction and scrubbing operations. We do those in the background here ourselves. We don't need a server to do that for us. No reason to drag the data out to compact the data. Additionally, there's the ability to, when data is written, it can be written in a chain of drives, where this can write to this one, then to this one, then to this one, back. And now you know when you write the data, if you get an acknowledgement back, you know it's on 3 different drives. SAS drive. Kinetic drive. Kinetic drive. It looks like a regular disk drive. It looks exactly the same size, same standard form factor. There's a lot of reasons for that. One of the biggest reasons is we have factories that turn out almost 1 million of these things every single day of the year. And to change the form factor would be awkward. This has 2 SAS ports that go at 6 gigs. This goes at 2 Ethernet ports that go at 1 gig. And in the future, it's going to be going at 2.5 and even 10 gigs over the same pins that are on this. There's a SCSI command set where you say data, read LBA count, gives you data. This says what? Oh, good drive. Okay.
We got 999,999 left that we built today.
Thank you. I'll do that with my mechanical sample now. My mechanical sample. SCSI command set read LBA count gives you data. Get key gives you value. Pretty simple. Applications love it. Write LBA count data, put key and value. There's actually additional metadata here that I'll talk about later, but they're put key and value. Delete key. How many people know about the trim command? Right? Is it pleasant? No, it sucks. Because it's all about preserving compatibility with the past. POSIX was written on top of a sectored device. The foundation of POSIX was the file system that was on Multics. was invented in 1965 because they had a random read-write thing that had a mailbox number for every glob of data. Now, that paradigm is still with us today, and there's no reason for it. We are spending millions of lines of code in the drives today to maintain compatibility with the past. This system wipes that away and gives the drive a lot higher value level of information so that it can manage the data in a smarter way, including knowing when a sector doesn't contain anything that is of value. Delete a key. Additionally, the size of the key is from 1 byte to 4 kilobytes. Now, 2 to the 8 to the 4096 is a large number of keys. So, in essence, it's an infinite key space. And you don't have to actually use it. Most people will usually have a key length in the 10s or 20s or maybe 100 bytes or so. That's normal, but we made it 4 kilobytes just because we didn't want somebody to come back to and say, okay, I want something larger. And that's just annoying. We have a value. The value is from 0 bytes to 1 megabyte. 1 megabyte is 1024 times 1024. Not this silly 10000000. Not a disk drive megabyte, a real computer megabyte. And there's a reason for this value to be 1 megabyte. And the reason is this. If you were to be allowed to send a terabyte to one disk, I have a lot of housekeeping I got to do. I got to reserve the space. I got to lay the data out. I got to do all kinds of weird stuff. It is so easy to turn around and say, break the data up into megabyte chunks. If I have a movie that's 2.5 gigabytes long, I have a movie. It's pretty easy to say, say the movie's Alien. So the first megabyte should be Alien, 0001. And the second megabyte should be Alien, 0002. And so on and so forth to Alien, 2000 for 2000 megabytes into the file. And it's very easy to do. And the value is the following. When we store the data on the disk, we store the data in temporal order. We get really fast write performance because when the data comes in, we stream it to the disk. Just write it away. POSIX is exactly the opposite. POSIX must put the data in its final resting place the first time. That's why it takes so much time to create a file, because it's doing all of the work in advance, so it never has to do anything after the fact. Current technology today really focuses on doing things first and then reorganizing it later. So it's a log-structured storage system that's down on the drive.
So, I'm not saying that's a wrong choice. I understand why you make it, but isn't that somewhat of a leafy abstraction to say that now the application talking to the Kinetic API has to actually understand that, this particular storage media can implement it efficiently at 1 megabit, so I have to break it on the client side.
Putting terabytes down on a single device is horrible. You got to have a breakpoint somewhere. So that the 1 megabyte, you're talking about the 1 megabyte limit. You have to break it somewhere. If you look at Amazon S3, they break it at what, 500 megabytes. Everybody has to have a chunk size because believe me, I worked on a network that had an infinite record length, an infinite network PDU length, and it's just painful. So.
I understand, but I guess the point that I'm trying to make is that, like S3, like we do with Swift, 5 gigabyte chunk size there. But saying that what's the difference in saying that your protocol buffers can have a payload of 1 megabyte as opposed to saying that my sector size is 4K?
It's only a factor of what?
No, the
10,000 larger?
That's my point.
What?
So what happens in 5 years when you change that?
I doubt it. We'll only make it larger. So I don't know. I think from 4K to 1 megabyte's a pretty big jump. It's not like I'm saying it's 8 kilobytes now. That would be annoying. On SAS, they have CRCs they're very small CRCs on each sector. But it turns out that with this, I'll talk more about this in the security section, but we have a full end-to-end data integrity where the data is written with the hash of the data it's written. And when you read the data, we will return that hash back to the application. So there really is end-to-end data integrity. Additionally, the drive, routinely, when it scrubs the data, the drive itself will go down there and check your end-to-end data integrity and tell you whether or not there's been silent data corruption or not. You don't have to read the data back and read it, compute it, and throw it away. We're going to talk about this some more a little later. This is, that box over there is right here. Here's a Dell box they're not here. That's another drive right there, doesn't matter. Two more pictures is a picture of a box that's a box from Huawei, and that's a box from Hive, and the board for that is over there. And just in summary, the drive itself is a network remote procedure call to a key value database. Data is pre-indexed, it could be compressed, it could do all kinds of wonderful things because underneath that API, we own the data. We are responsible for the care and feeding of the data. We have peer-to-peer copy, drive-to-drive copy of key rings. It doesn't even have to be a drive. How about a Kinetic SSD? You could move the data from drive to SSD or SSD to drive using the Kinetic Protocol. You just pass down a copy command, copy the data over there. It uses existing data center plumbing. No special changes to the networking in the data center, period. And that's a really hard thing that we did. We had to step back from a lot of things we could have done in these fancy networking things, but the one thing we don't need data center Ethernet, we don't need FCOE, we don't need, name all of the other standards that have been being worked on for the last 10 years that nobody will ever see the light of day. So it uses existing data center plumbers, it allows multiple masters, it allows data sharing between the drives, it has configurable caching per command. In a disk drive today, you have a flag that says, this drive can do write-back caching, right? If you have a battery backed up RAM or blah, 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 you can do that. But here we put it on every single command. There's a flag that says, this data, you can defer giving me an acknowledgement that the data is flushed until later, okay? I want to write a movie, 2,000 megabytes long, and I only care if the entire movie makes it to the drive. If one block is missing, I want to know that. If power fails during that data transfer, I don't care. I don't care because I didn't get the final acknowledgement that all the data is there. So you can say write back for the first 1,999 blocks, and then on the last one you can say flush. You'll guarantee that when you get that flush back, all those pending blocks are safe on the disk, and if power fails after you get the flush back, the data is still safe. You can say right through, and when you get the acknowledgement back, it is on the disk. Or it is somewhere protected. We don't even have to tell you how. It just will guarantee, we will guarantee to you that the data will be safe, even in the event of a power failure. And obviously we do our own space management. Why not? To separate the Kinetic drive from the Kinetic system, clustering, large-scale applications like S3 or Swift, and centralized management are all available, are things that we don't take responsibility for, but we give you the features and the ability so that when you put together a Kinetic system, the system cost is dramatically lower than using conventional drives. So a typical HA system in a cloud data center might be, this is supposed to be 60 drives, 2 SAS switches, a couple of Intel servers. Now whether those servers are here or plugged into the back here, it doesn't really matter. 2 servers, these SAS switches go to 2 servers, those 2 servers talk to the top of the rack switch. The value is we've taken the heavy lifting that these servers have been doing are now moved down into the drives, and the drives themselves can talk directly to the top of the rack switch. So on the back of the newest device, or on the front of this device, you have 10 gigs, and those 10 gig interfaces typically will go straight to the top of the rack switch.
Where's the application? You just
Somewhere else in the network.
Well, before I was running my application on the same server.
Before, you typically had a client that was living somewhere in the network. That client was going across the internal cloud data center. This is not intended for Joe's Pizza Shop, that his entire cloud data center is in the single rack. This is really focused on scale out storage. And in scale out storage, typically you have, in Swift, this would be the Swift proxy. In Hadoop, this would be the Hadoop system, because disaggregation in Hadoop is the current trend. In many cases, you'll have the client and the storage in different racks, so the client will talk to the front end, or the Swift proxy will talk across the data center router through the top of the rack down to the object node or the data node, and that data node will have a SAS cable to a SAS shelf. That's normally the way it's done. Okay, we don't know a single scale-out storage system that isn't done this way. Okay. With Kinetic, those servers are gone. Now you have more drives on the shelf. The client hasn't changed. The client's still over there. It has a different code load in it, different library. So instead of talking the object storage protocol that was with the previous system, they're talking directly to the Kinetic drive. I mentioned before that sequential write is about 50 megabytes per second. When you're writing keys that are in sequence, key A1, key A2, A3, A4, A5, you get about 50 megabytes per second with 1 megabyte files. Random write, 50 megabytes per second. We're log structured. When the data comes in, we write it out. So we get random writes of 50 megabytes per second at megabyte writes. For sequential reads, we get 50 megabytes per second. It's pretty consistent. And we found that most cloud storage systems, 50 megabytes per second at the file system level. Okay? This beats the daylights out of file system level accesses to disk drives today. Most times they get a lot lower than this, maybe 10 or 15 megabytes per second. Random read, a random read on a disk drive, a random get on a Kinetic drive, a random get will be about 20% slower than a traditional drive, because 20% of the time it has to do 2 seeks. Doesn't really matter. But what really matters is the fact that if you compare the time to get an individual key in a value out of a disk drive versus POSIX, open a file, read, if you compare that to a POSIX read, this is insanely faster.
Is that the difference in time to read the whole stream, or is that the time to first byte?
Time to first byte. And notice it says sequential read here. Even if I wrote the data randomly, over time we will organize the data in the background, and then random writes become sequential reads. And additionally, you have some great tools where you can actually say, I don't know what the next key is in this space, because the keys are ordered. I don't know the next key. I don't know what it is. Just tell me what the next one is. Or tell me, list for me all of the keys between A and B. We don't even know how people are going to use these features, but even in SwiftStack's case, it was amazing, because they said the key name in Swift is the object name, followed by the timestamp the object was written, followed by the block number. And they just took that name and they said, okay, add one to just go past that name in the logical space and say, give me the previous one. And that tells them when the most recent file was written. And that's kind of crazy. I think it's crazy. It's fun, but it's crazy. It helps them do their job.
Also, we don't have to do the whole directory structure nesting system practice.
Yeah.
So, are you assuming 1 megabyte data size here? All your numbers are based on 1 megabyte?
Yeah. Except this number, that's not based on that. But at 1 megabyte sizes, we're getting this, 50 IOPS. Okay? At 10 byte, these numbers are 1,500 IOPS. We can do 1,500 IOs per second for a drive, with the exception of random read. Random read is slower. That's why a flash-based Kinetic is such a compelling product. The API allows data movement, get, put, delete, get next, get previous. It has version, equal version for success. The range operations tell me all the keys between A and B. Multiple masters, it allows multiple masters, and I'll talk about the authentication, the integrity, and the authorization in a few minutes. Talk about that. It really is clusterable. We don't understand how the devices are clustered, but we provide some techniques to help the drive live inside of a cluster. One of the biggest problems in a cluster is dealing with something called split brain or zombie. Okay, well, a zombie in Computer-esque is a machine that you think has died, so you took it out of the configuration, and then it wakes up again, and now it's using the wrong configuration for a period of time. We have an interlock on the device so that every single command has what's called a cluster version, which is, we don't know what this number means, it's just a number. That number on the request and the drive must match. If they match, everything happens just fine. If you want to change the configuration because you're a Paxos system or you want to add more disk drives or whatever, you change the cluster number in the drives will reject any client that comes in with a bad cluster. That way, very high integrity. Peer-to-peer copy, and we have a full suite of management commands that go all the way from, is the drive healthy? What's your temperature? What's your utilization? How's your day going? So we have gets, puts, we have management commands, and we also have at the bottom, we have the ability now in the open source. I gotta get my mind about the features that are coming versus the features that are here. You actually can reach down to the drive and pull out the low-level bytes that are proprietary to the drive too. So that's not something that's normally question.
I'm talking on the range operation. So when range operation comes for a certain range, do you traverse the whole block structure file system from key 1 to key n, or how do you?
If you say, tell me the get range is to get the keys within a range. And the get range is limited to 200 keys. So if you say get all the keys in the drive, it will work for a little while and then give you the first 200 keys in the drive.
Oh, the range. So basically it has to scan.
It doesn't scan the whole thing. It's proprietary. It doesn't scan the whole thing.
Okay.
It's not stupid. We do a lot of work. This is not a hash database, but we do a lot of work to make sure that the system is both fast, log structured, fast, and yet the keys are ordered. The ordering of the keys is a very valuable feature. So one of the questions is, how do you bootstrap the system? Okay? I take this tray, I power it up, and I plug it into a network. What happens? This has 30 drives.
That one has 30 drives.
5, 3, 30 drives in there. So what's going to happen is these 30 drives are going to wake up, power up. They're going to go out to the DHCP server and say, I need an IP address. In some cloud data centers, that will actually be pre-configured with MAC addresses and...
Recording started.
You're annoying.
Yeah.
Okay. In some cloud data centers, they actually map the MAC address to the IP address. It doesn't really matter. The drive comes up. The drive gets an IP address for each interface. So every drive gets 2 IP addresses. Or each drive gets 2 IPv6 addresses. It's your choice. If the DHCP server serves up IPv4 addresses, it's an IPv4 device. If it serves up IPv6 addresses, it's an IPv6 device. Additionally, typically in the tray, you'll probably have a BMC or some other management processor. It will also request an IP address. Once that happens, there will be a ping message or a broadcast message to a well-known IP address or to an address that was provided by this server, either one, to send to a management server to say, hey, I'm a brand new drive. Nobody's ever seen me before. I'm coming into your configuration for the first time. What should I do? Then the management server comes down and will configure the devices with owners. Who owns this device? Here are the set of identities and keys that prove these identities on who owns this device. Okay? At which point, all of the object server apps are communicated with their keys and all these wonderful other things, and now the data flows read and write. So this is how you bootstrap a device in an existing data center. You bring in a brand new device over here. While this is up and running, you bring in a new device. It does the same thing. And no flag days to change configurations. I'll give you an example now for HDFS. In HDFS, you might have a client, a name node, and normally the way HDFS works is the client says, I want to open up file foo. It sends a request to the name node. The name node says, the data for file foo is on this data node and on that disk. Okay? So they use a protocol between the client and the data node to actually transfer the data, and then they use SAS and a file system to write the data to the disk. In a Kinetic version of HDFS, the client is changed, so instead of talking this protocol or this protocol, it talks the Kinetic protocol and comes down and puts the data on Kinetic. So in this case, a blob in HDFS's case may be 256 megabytes. And in this case, when it writes it to here, it will write it as 256 1 megabyte chunks. And we did calculations on how much difference the performance was. The performance is about 2 extra packets for every 700 data packets. Okay? The overhead is not high. Additionally, the data will flow direct, and the data node daemon, which is now no longer in the way, it doesn't need to be involved in the data transfers anymore, and it just monitors the health of the drive, the temperature, and all, how full are you, how busy are you, et cetera, et cetera, et cetera. The existing traffic goes from the client across TCP IP to the data node, across SAS to the disk. And in the future, it just goes, data is already going over TCP IP, now it just goes over TCP IP directly to the drive. It's that simple. Another area that I hate file systems. I hate POSIX. I think it's time to die. That's my personal opinion. This is a Swift benchmark that was done in EVault here almost a year and a half ago. About a year ago, where we counted every single SCSI command that went to a drive. Well, actually went to 180 drives. And we give you the sample of 3 drives. We took all of these operations and we categorized them by the length of the operation. In this case, we counted all of the operations and a cumulative count, operations by operation length, showing all of the operations, and then we also took the same information and now this time created a cumulative graph by how much data was transferred, organized by data length. So we found out that 92% of the IOs to the disk drive, 92%, 12 IOs to the drive for doing metadata operations for 1/2 megabyte write. Okay, the net throughput of the system was about 12 megabytes per second. And they thought that was pretty good. Okay, now we really wanted to know what's going on here. So we then visualized this in a different way. This is a strip chart of what was going on in the drive from the beginning on. And this is the sector location on the drive, the location. It was a 3 terabyte drive, and this was the location, the sector number. Okay? And the vertical axis is the length of the operation. So this is clearly the 500 kilobyte writes. This was a benchmark where we were running 60% writes of 20 megabyte files and 40% reads of 20 megabyte files. All the files were 20 megabytes. There was not a single file that was not 20 megabytes. And look at all those other operations. They have no value. You know, and it may be on a computer that's only this far away, but those operations are taking the head away from the data. And there were 12 of these for every single one of those. And that was annoying. We call this the silly stuff. We expect this number on Swift to go from 92% for 20 megabyte files to 10%. Where they do have small metadata operations that they need to do for their user metadata, like where is this file so you can do an LS on it. There is some of that kind of little metadata, but that's the application metadata. That's not this is mostly the file system metadata, managing free space and all these other things. So that's getting rid of the POSIX file system. Yeah, what is storage good for? Right? You write something, you get it back. You need enough organization to get your job done. And a flat namespace with an infinite-sized directory, effectively, works. Just name it what you want to name it. How much time?
You're out of it.
Tough.
Go ahead. Just keep finishing.
So, I'll skip a slide, just for you. This is working code. This is Hello World in Kinetic. This brings up a client. When you get here, you already have a client. No connect to a driver, no IOCTLs, no nothing, just connect to a client. A key, this is the key, the bytes hello, and the value is the bytes world. These are bytes, byte arrays. The keys and the values are byte arrays, octets. And no, you can't have 10-bit words. You can't have 6-bit words. They're 8 bits, okay? That's the only thing we can agree on. Okay, an entry, which is a key and a value, could have other metadata like the data integrity hash, a timestamp to make sure you can do atomic operations and so on. And here you say put force that entry. Force just says, I don't care what's already there, put this. But you could also say normal put, and it'll basically check to make sure it's the version that's there is okay. Entry get value. And it turns out that entry value will now say world. It's that simple. Oh yeah, and then you can delete the entry and close the connection. Oh, that's an extra line of code that doesn't work. Conclusion, it really is the next generation storage device. It really does disintermediate cloud applications from the drive. All of those layers that used to be below your cloud application are really gone. Really, really gone. It enables innovation for us inside of the drive. We really feel that this interface will allow us to get higher densities faster, which means lower cost per gigabyte for you in the long run. We believe it's lower total cost of ownership. Why? Because you're given less money to Intel. Use those Intel processors for what they're good for. They are really good application processors. Using an Intel processor to bring data from Ethernet and put it on SAS is a waste of your money. Intel likes that money, but it's a waste of your money because it's not adding value to the information. Applications add value to the information by processing the information. Copying it from one interface to another is not value. We have integration with Swift, HDFS, Bash React, Ceph, and Scality today. And what's amazing...
At the tone, please record your message. When you have finished press 1 for more options.
I need more beer.
That is weird.
I'll tell you what's amazing. We keep getting messages once in a while. So-and-so says, we got the system working. And we didn't even know who they are. We don't even know what they're doing. They never even copied. They just went to the open source. They downloaded the source. They started working with it. It's crazy. By the way, I'm going to put an advertisement for one. There is a POSIX file system on Seagate, github.com/Seagate/h-flat, which is a complete POSIX file system on top of Kinetic, even though I think POSIX should die. But it's very interesting. For more information, you go to Seagate.com, Kinetic, or developers.seagate.com. These are both the same place. Or you get the source code at github.com/Seagate. And for all of these, there are communities. Send in an issue, send in a comment, do whatever you want to do. Hey, bring the code down, make a change, send a pull request. It's a community. It really is a community. So I'm going to talk very quickly about security in the device because I was asked to talk about security. This time I've never actually talked about the security in the device. I'm very proud of it because security is a feature number one of the device. It's not a painted on, add-on. It is feature number one of the device. The Kinetic Protocol has several ways that it provides security. The protocol itself provides security. The data is over various transports that also provide security or don't. And the last is the drive security itself. The Kinetic Protocol knows the identity of the client. Not the IP address, not some white list, not some black list. It knows the identity of the client because when the data is sent, the request is signed with something called an HMAC. HMAC, Hash Mandatory Access Control. Okay? And that proves the integrity of the command. It proves the integrity of who the client is. So we know who the person is, and we know the command has authenticity. You remember I mentioned end-to-end data integrity? The tag for the end-to-end data integrity is in the command. So the command and the data are covered by high integrity for the authentication. And it's high integrity for the requests and the responses. Okay? Additionally, since we have a strong authentication of who is calling, we have a set of roles that each of the identities can do. One can do gets, someone else can do puts. Hey, why not? That's kind of cool. One machine you don't trust to read the data, but you trust to send the data. Maybe it's a sensor. And even if that sensor gets hacked and somebody says, okay, I want you to go read the data, sensor, and you turn around and say, no, I'm sorry, sensor, you can't read data, you can only write it. And then the person that can only read data can't write data. Think of forensics, think about other things where you can read the data, but you're not allowed to write it. So that kind of makes sense. The management nodes have a management role, and the security nodes have a security role. This meets the criteria for FIP certified. This is not FIP certified. It will probably someday will be FIP certified, but these roles are necessary to be able to do something like be FIP certified. We also have replay prevention. Replay prevention. Okay, here's a question for anybody. Class, is it possible to take information and insert it maliciously into a TCP/IP stream? Yes, yes, very easy, very trivial, and actually quite fun. Replay prevention, so a message is inside of a session. If you take something and say, okay, I delete a record, I add a new record. But somebody grabs the delete out of the stream that it saw and then replays the delete again, it will not work. There's sequence numbers, there are connection IDs and sequence numbers inside of every session, all covered by the integrity checks.
Is this basically serverless?
No, no tickets yet. This is just a shared secret. There's a shared secret between every drive and the clients. Every identity has a secret that it uses to key its HMAC. Every drive knows all of the keys for all of the identities that are allowed to talk to this drive.
How are those managed?
What?
How are those managed?
By the upper layer protocol that we don't do.
You just answered my question.
Well, I'm glad.
How many keys?
Hundreds. Thousands. We haven't had a problem yet with somebody saying we didn't have enough. Now, there are two transports to the device. In other words, you can open up two TCP/IP sockets to the device. One of the transports is port 8123, and the other is port 8444. 8444 is TLS, full TLS with certificates that are anchored in Seagate.com. And when HDST comes out with their Kinetic device, it will be anchored in HDST.com. I'm just teasing you. But the normal clear text port for people that aren't concerned about performance or people that have already encrypted their data, for me, I personally find end-to-end data encryption is better instead of encrypting the data to the drive, decrypting the data, and then re-encrypting the data and then putting it on the disk, which is what happens over this port. What might be better was, since the commands themselves have no value, if you encrypt the values themselves, then you could even encrypt the keys. That doesn't matter. You could even store the data in the encrypted form. We don't care. So both of these are possible. And the normal client is not recommended for configuration information or setting the security parameters and other things. Okay? In terms of drive security, there is instant secure erase. And it's a cryptographic erase. The entire configuration of the drive and all customer data is all gone in a matter of milliseconds. Okay? And it's a quick return to factory defaults. It's almost a remanufacture. So that if everybody works for vendors in here, most people work for vendors in here. If you want to run a suite of benchmarks, in between the benchmarks, run this, and it will return the device. It will totally defragment the device, and the device comes back to a pristine condition. TLS again. Oh, sorry, that was a cut and paste problem on my part. The drives will also have pin unlocking. They don't have it today, but they will also have pin unlocking, so that when the device powers up, it will require a pin to unlock the device, so that you can get the kind of security features that Seagate has on their SED drives. I'm done. Now, since you've all been listening quietly and not asking questions, you can ask questions now.
So what is the largest cloud implemented using this Kinetic drives?
What's our largest configuration? Considering this device has not actually been announced yet, we currently have about 3,000 drives in the field. Not in one ring. No, but we have a lot of proof of concepts that are in process that are scaling up to hundreds and soon thousands in a single configuration.
The clustering is probably the largest order of it.
Okay.
Yeah, so you mentioned that everything is logical underneath.
Everything is.
Log structure underneath.
Yeah.
When does compaction happen?
Okay. It's not in the protocol yet, but it will be soon. Compaction in a large-scale cloud storage system, the problem is anything that scales out, the performance of the scale-out system is dominated by the performance of the slowest device. So a device doing compaction on its own is bad. Because one device will be doing compaction, it will be slow, everybody else will be fast, but the whole system will be slow. So we're adding another series of commands to allow the system to decide when and how much and at what priority the compaction should occur. And so basically there will be the ability of the system to control the priority of the compaction and when it happens.
So basically compaction will be manually triggered by the administrator or by the system.
The what?
So basically compaction will be manually triggered by the
Yes.
administrator or the
Yes.
system or something like that.
Yes. And the reason, here's the reason. Basically you will say, I want you to compact the disk drive from the first key to the last key. And I want you to do this for 30 seconds at a low priority, and let me know when you're done. Now, in 30 seconds, you're not going to scan the entire drive. In 30 seconds, you got this far. At the end of that time, we will say, we got this far, and we found nothing. Or we got this far, and we had this broken key. And then you step and repeat. Most systems already ping devices every 30 seconds anyway to determine whether they're healthy or not. This does not add significant overhead to the system.
You have benchmarks showing your performance during compaction.
Yes, we actually right now we do compaction. Right now we do compaction in real time. We don't manually trigger it now, and we fill the disk drives and we start filling at 60 megabytes per second, and when the drive is full, we're at 40 megabytes per second. So we don't have a problem with compaction because it's doing compaction while we're filling it.
You have latency measurements are based on this histogram while compaction is going on. So that's the most interesting bit.
The latency issues. I don't have that, but it's not long. It really isn't, because compaction is the lowest priority. And so the only thing that you can have is that there is a seek going on to somebody else. And so the maximum impact is one seek, which is 10 milliseconds. No, I'm done. No! Go ahead.
So I saw in your Hello World couple days you have like, big key, and like close connection. There's also a way of doing fsync.
Okay, flush. There is a flush command. And there's also a command that you can write the data with a flush as a flag. Either way, both work.
Okay, so that actually will call fsync on the drive.
The assumption that we have a file system underneath the Kinetic daemon is an assumption that I'm not going to tell you if it's true or not.
Sorry, I mean, just for sure. I mean,
It's like for sure, for sure, guaranteed, for sure, for sure. Hey, I'm from the valley, okay? Absolutely true.
Sorry, just to clarify, so there's some way of saying this is definitely on, persisted on the drive.
Yes.
Not buffer.
Yes.
Okay.
There are two ways. Number one, okay, you write the data with write through. It is guaranteed that when you get the write back, that data is persistent on disk. You can write the data with flush. You're guaranteed that when that command returns, there is no dirty data in RAM. Okay? You can also call the calls that says flush. And when that returns, there's guaranteed there's no data on, no dirty data in the RAM. And I'll go ahead. Yeah.
So this is unrelated to the flush and compact. So the performance of sequential read, you said it's 50 Mbps because the data is ordered eventually.
Mm-hmm.
So the numbers that you have provided is not immediately after.
Yes,
random
immediately.
write, right? You have given it sufficient time to reorder the keys and then you have measured the.
Correct. But let's imagine this. I stream the data in a certain key order. A, Z, B, W, random order. And then I went immediately back to read it in that order. A, Z, B, W. It'll be 50 megabytes per second. When we write it, it's in temporal or time order. If you read it immediately and read it in time order, it will be fast.
But in reality, the writes will continue to come when the application is issuing a sequential rate, right? So application will never get 50 Mbps in sequential rate because writes are going to, it's not going to be pure.
Honestly, we're a disk drive vendor. We have hundreds of engineers working on this, and this is something we test all the time, and we focused on, and performance is a key feature of Seagate products. So, maybe it's hard, but it's something we do. Additionally, let me tell you something else we do. Pissed me off. But this is something else we do. We will write keys and values to the drive, and at random points power fail the drive. Then we will bring the drive back up, and we will go and read the data and make sure that our internal database is not corrupted, and that for every write that we said completed, we have that still on the drive. So they do those kinds of tests all the time. That's what they do. Oh, and one of the other items that Seagate does, it's amazing. One of the tests before GA is to run 1,000 drives for 1,000 hours and no failures.
I'm not sure if the way I interpreted that question was, do you have any numbers for 60-40?
Of 60-40?
60-40 random, 60% rate.
The workload mix test.
Yeah.
I I don't have a workload mix test because there's so many of them.
But any,
I write them, and I can't explain them right now. Would you like 4 drives and run your test?
If I can get
Give your card to Allie on the way out.
Can you describe the pin and set pin usage?
Pen?
The pin and set pin usage. Can you
Yes.
set up message?
That section of the message is going to change soon. Okay, that's the first item. The second item is there's 2 pins in the drive. One pin will be to unlock the drive. If the drive ever lost power, it requires a pin to unlock. That is to protect the drive from somebody reaching into the drive. I won't do it again, Jeff. And taking out the drive and then getting all the data, because when you withdrew the drive, it powered off, and now you need the pin to power it on again, just like SED. The second pin that's in the drive is the instant cryptographic erase pin. Those pins, they can be the same, heaven forbid, but normally they're different. So there will be 2 pins, and there will be a better way than what's in the protocol right now.
So going back to the example you just gave, like you have written the keys in time order, like A, Z, C, B,
Yeah.
whatever, right? And if you immediately issue a range operation saying give me keys A through Z,
And I will give them to you in order.
give me in order.
Yep.
But then basically you will be reading in the same time order. And
How I do that, I'm not telling you. Because my competition's in the room.
We don't like key value anyway, so.
No competition then.
How many connections?
Hundreds. Hundreds per drive. Now, we're working on a callback, a connect back, so that you could make the request with UDP, and then the drive will connect back and do sort of like an RDMA operation. We're working on that, but hundreds. When the data is written in a put operation, a end-to-end data integrity field is there, so that when you issue the put, the data integrity goes along with the data and is stored with the data. Periodically, the drive will wake up and test that data integrity and report if it's broken. But when you issue a GET, that data integrity comes back. So there is full end-to-end data integrity. We have MD5, SHA-1, SHA-2. You have to provide it.
Then drive it in the background, you'll do scan.
We'll do scan and check.
So what's the second port used for? I hear that for SAS it's
Both ports are identical. What? No, both ports, 8123 and 844 are identical. You can use either one. One of them is on TLS, one of them is not. Both Ethernets are identical. They're active, always on. So you can connect to either. And you can get 220 megabytes per second by connecting to both. There's no difference between either of the interfaces.
So you don't do Ethernet aggregation.
There is no bonding. Bonding would have required us to require changes to the customer data center network.
Sorry, being dumb. So can I access? So is it equivalent to having multiple channels for a single device?
Yes, it's like having a server with 2 A records.
Device reorder.
In the requests? Okay, our device right now does not reorder. In other words, the requests come down in a certain order. They will respond in a certain order. That is an artifact of implementation. It is not a requirement of the protocol.
The protocol going to add features to support the
Protocol doesn't need it. Reordering is implicit in the protocol. In other words, if I issue async gets, okay, I say get key foo and get key bar. Send them down to the drive. Foo was first, bar was second. Down to the drive. According to the protocol, The request for bar could come back first. The response to bar could come back first, and the response to foo could come back second.
For all reads, it's easy to figure out. You don't care.
All reads, all writes, everything. Doesn't matter.
Combinations of reads and writes get complicated. Why?
There's an argument as to why, and stay tuned. This is a community operation, and ask about these things in the community too. If you want to just send an email saying, what about ordering, what about batch operations, blah, 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 blah. Ask those questions and we'll give you answers. 2 more questions, and he's going to kick me off the stage.
Yeah.
He should have kicked me off before.
It's all right. Just good. We're just going questions in here.
Keys that you run?
Until the drive is full.
Right, but how many is there? How many can you do? Can you do the power? And if you do that many, if you have 100 million keys, how long does it take you to look up?
20% longer than a random seek.
Okay, so it's varied on how many?
Yes. There might be higher latency variations among that. There might be a little longer tail, but in general, the request will be quick.
And what's the queue depth, maximum queue depth for the requests?
About 20. This is a mechanical disk drive. Having more than 20 requests pending inside of a device with one arm doesn't make a lot of sense.
Yeah, but you said an SSD device is constant.
That an SSD device might have a different depth. The SSD device might have a depth of 100. I don't know about that device. It's not in the protocol. The specification of how deep the queue is not a protocol specification. It's a device implementation.
You mentioned that the traditional drives have like tens of megabytes of DRAM.
Yes.
You get the same.
No, we have a half a gigabyte.
I have a follow-up question about that 20% overhead over the traditional random bit over traditional drives. Is that for the 1 MB request size throughput?
Both.
Even the latency?
Yeah.
It's just 20%?
Yeah. So we read up on Bloom filters.
You mentioned low priority mode for action stack.
Yes.
You have a quality search support which I'm running the protocol.
Is there what?
Quality search support which I'm running the protocol.
Watch the protocol buffer, Kinetic Protocol repository. There will be something moving into there very soon.